Okay, I was looking at, so give me a second. I need to create a DSA. Group DSA code. Uh, yeah, I think those two will be suffice. Will suffice. Uh, don't need it. Yeah, I think this two will do it. Let's look at this. I was just interested in this. No, no, shut up. What was the doctor's? Why is the resolution fucking ass? Oh, What should we do? I wanna Ark of yeah. No, Ark of the Covenant. The fuck is fuck you? What the fuck am I looking at? This is retarded.
The brachycystic crone. And for the first 2/3 or so of the video, I'm just going to
The brachist the Crohn problem. Problem posed by Johann Bernoulli in the year 1696 asks for the path along which an object descends without friction from one given point to another, under only the influence of gravity in the shortest interval of time.
For this video, I'm doing something a little different. I got the chance to sit down with Stephen Strogatz and record a conversation. For those of you who don't know, Steve is a mathematician at Cornell. He's the author of several popular math books and a frequent contributor to, among other things, Radiolab and the New York Times. To put it shortly, he's one of the great mass communicators of math in our time. In our conversation, we talked about a lot of things, but it was all centering around this one very famous problem in the history of math, the brachistochrone. And for the first 2/3 or so of the video, I'm just going to play some of that conversation. We lay out the problem, talk about some of its history, and go through the solution by Johann Bernoulli from the 17th century. After that, I'm going to show this proof that Steve showed me. It's by a modern mathematician, Marc Levy, and it gives a certain geometric insight to Johann Bernoulli's original solution. Then at the very end, I have a little challenge for you. We should probably start off by just defining the problem itself.
Okay. All right. You want me to take a crack at that?
Yeah, go for it.
Okay. Yeah. So it's this complicated word, first of all, brachistochrone, that comes from two, I have to check. Are those Latin or Greek words? I think.
I'm pretty sure they're Greek.
Okay. So Greek words for the shortest time. And it refers to a question that was posed by one of the Bernoulli brothers, by Johann Bernoulli. If you imagine like a chute and there's a particle moving down a chute, being pulled by gravity, what's the path of the chute that connects 2 points so that it goes from point A to point B in the shortest amount of time?
I think what I like most about this problem is that it's relatively easy to describe qualitatively what you're going for. You know, you want the path to be short, something like a straight line, but you want the object to get going fast, which requires starting steeply, and that adds length to your line. But making this quantitative and actually finding the balance with a specific curve, it's not at all obvious and makes for a really interesting problem.
It is. It's a really interesting thing. I mean, most people, when they first hear it, assume that the shortest path will give the shortest time, that the straight line is the best. But as you say, it can help to build up some steam by rolling straight down at first, or not necessarily rolling. I mean, you could picture it sliding. That doesn't really matter how we phrase it. But so Galileo had thought about this himself much earlier than Johann Bernoulli in 1638. And Galileo thought that an arc of a circle would be the best thing. So he had the idea that a bit of curvature might help.
And it turns out that the arc of the circle is not the right answer. It's good, but there are better solutions. And the history of real solutions starts with Johann Bernoulli posing this as a challenge.
So that's then in June of 1696. And he posed it as a challenge really to the mathematical world at that time. For him, that meant the mathematicians of Europe. And in particular, he was very concerned to show off that he was smarter than his brother, So he had a brother, Jacob, and the two of them were quite bitter rivals, actually, both tremendous mathematicians. But Johann Bernoulli fancied himself the greatest mathematician of his era, not just better than his brother, but I think he thought that he might be better than Leibniz, who was alive at the time, and Isaac Newton, who was by then sort of an old man, more or less retired from doing math. Newton was the warden of the mint, be something like Secretary of the Treasury nowadays.
And Newton shows him up, right? He stays up all night and solves it, even though it took Johann Bernoulli 2 weeks to solve.
That's the great story, that Newton was shown the problem, wasn't really pleased to be challenged, especially by somebody that he considered beneath him. He considered pretty much everybody beneath him. but yeah, Newton stayed up all night, solved it, and then sent it in anonymously to the Philosophical Transactions, the journal at the time. And it was published anonymously. And so Newton complained in a letter to a friend of his. He said, "I do not love to be dunned and teased by foreigners about mathematical things." So he didn't enjoy this challenge, but he did solve it. The famous legend is that Johann Bernoulli, on seeing this anonymous solution, said, "I recognize the lion by his claw." I don't know if that's true, but it's a great story. Everyone loves to tell that story.
And I suspect part of the reason that Johann was so eager to challenge other mathematicians like Newton is he secretly knew that his own solution was unusually clever. Maybe we should start going into what he does.
Yes, he imagines that to solve the problem, you let light take care of it for you, because Fermat in the early 1600s had shown that you could state the way that light travels, whether bouncing off of a mirror or refracting from air into water where it bends or going through a lens. All the motion of light could be understood by saying that light takes whatever path gets it from point A to point B in the shortest time.
Which is a really awesome perspective when you think about it, because usually you think very locally in terms of what happens to a particle at each specific point. This steps back and looks at all possible paths and says nature chooses the best one.
Yes, it is. It's a beautiful and as you say, really an awe-inspiring mental shift. For some people, literally awe-inspiring in the sense that it had religious overtones, that somehow nature is imbued with this property of doing the most efficient thing.
Oh, interesting.
But leaving that aside, you could just say it's an empirical fact that that is how light behaves. And so Johann Bernoulli's idea was to then use Fermat's principle of least time and say, let's pretend that instead of a particle sliding down a chute, it's light traveling through media of different index of refraction, meaning that the light would go at different speeds as it successively went sort of down the chute.
And I think before we dive into that case, we should look at something simpler. At this point in the conversation, we talked for a while about Snell's law. This is a result in physics that describes how light bends when it goes from one material into another, where its speed changes. I made a separate video out of this, talking about how you can prove it using Fermat's principle, together with a very neat argument using imaginary constant tension springs. But for now, all you need to know is the statement of Snell's law itself. When a beam of light passes from one medium into another, and you consider the angle that it makes with a line perpendicular to the boundary between those two materials, the sine of that angle, divided by the speed of light, stays constant as you move from one medium to the next. So what Johann Bernoulli does is find a neat way to take advantage of that fact, this sine of theta over v stays constant fact, for the brachistochrone problem.
When he thinks about what's happening with the particle sliding down the chute, he notices that by conservation of energy, the velocity that the particle has will be proportional to the square root of the distance from the top.
And just to spell that out a little bit more, the loss in potential energy is its mass times the gravitational constant times y, that distance from the top. And when you set that equal to the kinetic energy, 1/2 times mv squared, and you rearrange, the velocity v will indeed end up being proportional to the square root of y.
Mm-hmm. Yes. So that then gives him the idea about, let's imagine glass of many different layers, each with a different velocity characteristic for the light in it. The velocity in the first one is v1, and the next one is v2, and the next one is v3, and these are all going to be proportional to the square root of y1 or y2 or y3.
And in principle, you should be thinking about a limiting process where you have infinitely many, infinitely thin layers, and this is kind of a continuous change for the speed of light.
Mm-hmm. And so then his question is, if light is always instantaneously obeying Snell's law as it goes from one medium to the next, so that v over sine theta is always a constant as I move from one layer to the next, what is that path where, such that these tangent lines are always instantaneously obeying Snell's law?
And for the record, we should probably just state exactly what that property is.
Okay.
So the conclusion that Johann made was that if you look at whatever the time minimizing curve is, and you take any point on that curve, the sine of the angle between the tangent line at that point and the vertical, divided by the square root of the vertical distance between that point and the start of the curve, that's going to be some constant independent of the point that you chose.
Mm-hmm.
And when Johann Bernoulli first saw this, correct me if I'm wrong, he just recognized it as the differential equation for a cycloid, the shape traced by the point on the rim of a rolling wheel. But it's not obvious, certainly not obvious to me, why this sine of theta over square root y property has anything to do with rolling wheels.
It's not at all obvious, but this is, again, the genius of Marc Levy to the rescue.
Do you want to say a few words about Marc Levy?
Yeah, well, Marc Levy is a very clever as well as a very nice guy who's a friend of mine and a terrific mathematician at Penn State, who has written a book called The Mathematical Mechanic, in which he uses principles of mechanics and more generally physics to solve all kinds of math problems. That is, rather than math in the service of science, it's science in the service of math. And as an example of the kinds of clever things that he does, he recently published a little note, very short, showing that if you look at the geometry of a cycloid, just drawing the correct lines in the right places, that this principle of velocity over sine theta being constant is built in to the motion of the cycloid itself.
So, in that conversation, we never actually talked about the details of the proof itself. It's kind of a hard thing to do without visuals. But I think a lot of you out there enjoy seeing the math, and not just talking about the math. It's also a really elegant little piece of geometry, so I'm going to go through it here. Imagine a wheel rolling on the ceiling, and picture a point P on the rim of that wheel. Mark Levy's first insight was that the point where the wheel touches the ceiling, that I'll call C, acts as this instantaneous center of rotation for the trajectory of P. It's as if, for that moment, P is on the end of a pendulum whose base is at C. Since the tangent line of any circle is always perpendicular to the radius, the tangent line of the cycloid path of P is perpendicular to the line PC. This gives us a right angle inside of the circle, and any right triangle inscribed in a circle must have the diameter as its hypotenuse. So from that, you can conclude that the tangent line always intersects the bottom of the circle. Now, let theta be the angle between this tangent line and the vertical. We get a pair of similar triangles, which I'll just show on the screen. You can see that the length of PC is the diameter times sine of theta. Using the second similar triangle, this length times sine of theta again gives the distance between P and the ceiling, the distance that we were calling y earlier. Rearranging this, we see that sine of theta divided by the square root of y is equal to 1 divided by the square root of the diameter. Since the diameter of a circle, of course, stays constant throughout the rotation, this implies that the sine of theta divided by square root of y is constant on a cycloid, and that's exactly the Snell's law property that we're looking for. So, when you combine Johann Bernoulli's insight with this little geometry proof, that's the cleverest solution of the brachistochrone that I've ever seen. And I could call it done here, but given that the whole history of this problem started with a challenge that Johann Bernoulli posed, I want to finish things off with a little challenge of my own. When I was playing around with the equations of a cycloid, something interesting popped out. Consider an object sliding down the cycloid due to gravity, and think about where it is along the curve as a function of time. Now think about how the curve is defined, as this trajectory of the point on a rim of a rotating wheel. How might you tweak the rate at which the wheel rotates, so that when the object starts sliding, the marked point on the rim of the You walk alone into a room and you find a chessboard. Each of the 64 squares has a coin sitting on top of it. And taking a step back, this is going to be one of those classic prisoner puzzles where a strangely math-obsessed warden offers you and a fellow inmate a chance for freedom, but only if the two of you solve some elaborate scheme that they've laid out. In this case, what they've done is carefully turned over each of the coins to be heads or tails according to whatever pattern they want it to be, and then they show you a key. They put that key inside one of the chessboard squares. Each square is a secret compartment or something like that, so you know where the key is. And the goal is going to be to get prisoner number 2 to also know where the key is. But the only thing that the warden allows you to do before you leave the room is to turn over one and only one of these coins. At that point, you walk out, your fellow prisoner walks in, and with no information other than the set of heads and tails that they're looking at, which you've only barely tweaked, they're supposed to deduce where the key is hidden, potentially winning freedom for the both of you. As is typical with these puzzles, the two of you can strategize ahead of time if you want, but you won't know what the specific layout of heads and tails is. And moreover, the warden can listen in on your strategy and do their absolute best to thwart it with some adversarial arrangement of the coins and the key. So, I first heard about this puzzle over dinner conversation actually at a wedding, and it just totally sucked me in. I remember the drive home was maybe 3 hours, and I think my mind was glued to the topic of flipping coins and encoding state that whole time. But the puzzle sticks with you even after that. After I solved it, I fell into these two surprisingly interesting rabbit holes. One was to prove that the challenge is actually impossible if you vary the setup a little bit, maybe making it a 6x6 chessboard, or maybe removing one of the squares. And to give you a little sense for where that rabbit hole leads, this video is going to end with an especially pleasing way to paint the corners of a 4-dimensional cube. The other rabbit hole was to work out how closely you can connect the solution of this puzzle with error correction, which is a super important topic in computer science and information theory. The idea is that when computers send and store data, the messiness of the real world inevitably flips a bit now and then, and that can completely change how the data is read. So error correcting codes are a way to add a shockingly small amount of information to a message that makes it possible for the receiver to identify both when there is an error, and more impressively, precisely how to fix it. It turns out that the intuition for solving this puzzle is essentially the same as the intuition behind these things called Hamming codes, which are one of the earliest examples of highly efficient error correction. Which is all to say, time spent mulling over this problem is not as useless as you might think it is. Now, you and I aren't actually going to go through the solution here. Instead, I filmed a video all about that on Stand Up Maths with Matt Parker, who I'm sure many of you recognize from his combined YouTube and stand-up and book fame. We each talk through our thought process in solving it, and it's good fun, because there are multiple ways of looking at it. Instead, what I want to do with you here is take a more global view of every possible strategy for this puzzle, and bring you with me down that first rabbit hole of proving why certain variations necessarily leave room for the warden to thwart you, no matter how clever you are. The proof itself is one of those satisfying moments where you shift perspective and it reveals the solution, and the whole context leading up to it is a nice chance to practice reasoning about higher dimensional objects as a way to draw conclusions about information and data. Plus, it does more to help you appreciate the solution to the original puzzle when you can see how it is, in a sense, almost impossible. Where to start? What we want is some kind of visualization for what it even means to solve this puzzle. And to build up to the general case, let's knock things down to the simplest case that we can that still has any kind of meaning to it. 2 squares, 2 coins, and 2 possibilities for where the key is. One way that you could solve this is to simply let the second coin communicate where the key is. If it's tails, it means the key is in the left square. If it's heads, it means the key is in the right square. Not a big deal, right? It's one bit of information. So when you need to change that coin, you can flip it, but if you don't need to change it, you can just flip the other coin. First things first, let's stop thinking about these as heads and tails and start thinking of them as ones and zeros. That's much easier to do math with. Then you can think of these pairs of coins as a set of coordinates, where each of the 4 possible states that the board can be in sit at the corners of a unit square, like this. This might feel like a silly thing to do when we already know how to solve this case, but it's a good warm-up for turning the larger cases into a kind of geometry. Notice, flipping one of the coins moves you along an edge of the square, since it's only changing one of the coordinates. Our strategy of letting that second coin encode the key location could be drawn by associating the bottom 2 corners, where the y-coordinate is 0, with the key is under square 0 state. Which means those top 2 corners are associated with the key is under square 1 state. So think about what it means for our solution to actually work. It means that no matter where you start, if you're forced to take a step along an edge, forced to flip one of the coins, you can always guarantee that you end up in whichever of these 2 regions you want to. Now the question is, what does it look like for a bigger chessboard? The next simplest case would be 3 squares, 3 coins, and 3 possibilities for where the key is. This gives us 8 possible states that the coin can be in, and playing the same game that we did before, interpreting these states as coordinates, it brings us up into 3-dimensional space, with each state sitting at the corner of a unit cube. The usefulness in a picture like this is that it gives a very vivid meaning to the idea of turning over one of the coins. Every time you flip a coin, you're walking along the edge of a cube. Now, what would it mean for you and your fellow inmate to have a strategy for this puzzle? Whenever prisoner 2 walks into that room, they need to be able to associate the state that they're looking at, 3 bits basically, with one of 3 possible squares. We're already thinking very visually, so let's associate those squares with colors. Maybe red for square 0, green for square 1, and blue for square 2. In this conception, coming up with a strategy, any possible strategy, is the same thing as coloring each of the 8 corners of the cube, either red, green, or blue. So, for example, let's say you colored the whole cube red. Well, I don't know if you'd call this a strategy exactly, but it would correspond with always guessing that the key is under square 0. Let's say instead your strategy was to add the first 2 coins together and use that as an encoding for the key location. Well, then the cube would look like this. What's kind of fun is we can count how many total strategies exist. With 3 choices for the color of each vertex and 8 total vertices, we get 3 to the power 8. Or, if you're comfortable letting your mind stray to the thought of painting a 64-dimensional cube, you can have fun thinking about the sense in which there are 64 to the 2 to the 64 total possible strategies for the original puzzle. This is the size of the haystack when you're looking for the needle. Another attempt for the 3-square case might look like taking 0 times coin 0 plus 1 times coin 1 plus 2 times coin 2, and then reduce that sum mod 3 if you need to. Over on Stand Up Maths, Matt and I both talk about trying a version of this for the 64-square case, and why it works decently well for a random arrangement of coins, but why it's ultimately doomed. From our view over here, it just looks like one more way to color the cube, but it's worth taking a moment to walk through some of those corners. Let's say that you get into the room and all 3 coins are set to tails, so it's like you're starting at the corner 0, 0, 0. If you were to flip coin 0, that doesn't change the sum, so it takes you to another red corner. If you flipped coin 1, it increases the sum by 1, so it takes you to a green corner. And flipping coin 2 takes you up to 2, which looks like a blue corner. The fact that you always have access to whichever color you want is a reflection of the fact that this strategy will always win if this is the corner that you're starting on. On the other hand, let's say that you started at 0, 1, 0. Well, in that case, flipping coin 0 takes you to another green corner, since it doesn't change the sum. But flipping either coin 1 or coin 2 happen to take you to a red corner. There's simply no way to get to a blue corner. Basically, what's happening here is that you have the options to subtract 1 by turning off coin 1, or to add 2 by turning on coin 2. And if you're working mod 3, those are both actually the same operation. But that means that there's no way to change the sum to be 2. An adversarial warden who knows your strategy could start with this configuration, put the key under square 2, and call it done. But even without thinking about sums mod 3 or anything like that, whatever the implementation details, you can see this in our picture manifested as a corner that has 2 neighbors of the same color. If you don't have a bird's eye view of all possible strategies, when you find that any specific one of them just doesn't work, you're left to wonder, okay, maybe there's a sneaky clever strategy that I just haven't thought of yet. But when we're thinking about colors on the cube, you're naturally led to an interesting combinatorial question. Is there some way that you can paint this so that the 3 neighbors of any given vertex always represent red, green, and blue? Maybe it seems bizarre, even convoluted, to go from a puzzle with chessboards and coins to talking about painting corners of a cube, but this is actually a much more natural step than you might expect. I have talked with a lot of people about this puzzle, and what I love is that many of the experienced problem solvers immediately jump, unprompted, to talking about coloring the corners of a cube, as if it's a kind of de facto language for this puzzle. And it really is. Thinking about binary strings as vertices of a high-dimensional cube, with bit flips corresponding to edges, that actually comes up a lot, especially in coding theory, like the error correction stuff I referenced earlier. What's more, you often hear mathematicians talk about coloring things as a way to describe partitioning them into distinct sets. If you've ever heard of that hilariously enormous number Graham's constant, for example, the problem where that came up was also phrased in terms of assigning colors to a high-dimensional cube. Though, in that case, colors were given to pairs of vertices instead of individual ones. The point is, analyzing how to color a high-dimensional cube is more of a transferable skill than you might expect. So to our question, can you make it so that every vertex has a red, a green, and a blue neighbor? Remember, this is the same thing as having an encoding for key locations so that you're always one flip away from communicating whichever location you want to. It would actually be enlightening if you paused the video and tried this now. It's like a weird three-dimensional variant of a Sudoku. Very similar to Sudokus, in fact, in the sense that you want certain subsets to be filled with all three possible states. For example, you might start by painting one of the corners an arbitrary color, let's say red, and so you know that its three neighbors need to be red, green, and blue. Doesn't really matter how you do it. And then maybe we move to the red neighbor and say that the other two adjacencies need to be green and blue. Maybe we do it like this. But at least how I've drawn it here, you're stuck. You are unable to choose a correct color for the next two. Can you see why? What I'd like to share is a lovely little argument that explains not only why this will never work in 3 dimensions, but also why it can't work in any dimension that's not a power of 2. The idea is that the symmetry in the property that we're looking at will end up implying that there have to be an equal number of red, green, and blue vertices. But that would mean that there's 8/3 of each, which is not possible. And before I go on, pause, see if you can think of a way to solidify that intuition. It's a fun exercise in turning a vague instinct into a solid proof. Alright, you ready? One way to do this is to imagine a process where you go through each corner and you count how many of its neighbors are a particular color, say red. So each step here, we're looking at the 3 neighbors of a given vertex, counting up the red ones, and adding that to a total tally. For this specific coloring, that count came out to be 12, but if we had the property that we wanted, every corner would have exactly 1 red neighbor, so that count should be 8. On the other hand, every red corner is counted exactly 3 times, once for each instance where it's somebody's neighbor. So that final tally has to be 3 times the total number of red corners. So, it's simple. Find a coloring where 8/3 of the corners are red. Isn't that nice? Counting how many times some corner has a red neighbor is the same as counting how many times a red corner has some neighbor, and that's actually enough to get us a contradiction. What's also nice is that this argument immediately generalizes to higher dimensions. Think about solving the chessboard puzzle with n squares. Again, the puzzle is to associate each arrangement of coins with some state, some possible location for the key. And the goal is to make it so that the arrangements that you can get to with one flip of a coin represent all possible states, all possible places the warden might have hidden that key. Even if you can't visualize most higher dimensional cubes, we can still talk about things like vertices of such a cube and their neighbors, basically as a way to describe bit strings and the ones which are 1 bit flip away. Really, there's just 2 relevant facts you need to know. If you're standing at one of these vertices, you have n distinct neighbors, and the total number of vertices is 2 to the n, 1 for each bit string of length n. And from here, you can play the same game that we did in 3 dimensions. You can go through each corner and count how many red neighbors it has. If it's possible to do the coloring we want, this sum should be 2 to the n, 1 for each vertex. On the other hand, each red corner is counted once for each of its neighbors. So that means that we need to end up with n times the total number of red corners. Since that left-hand side is a power of 2, the right-hand side also has to be a power of 2, which could only ever happen if n itself is some smaller power of 2. So, for example, if we were in 4 dimensions, or 64 dimensions, there is no contradiction. It's at the very least possible to evenly divide the vertices among the different colors. To be clear, that is not the same thing as saying there necessarily is a solution for the power of 2 case. It's just that it can't be ruled out yet. To me, this is completely delightful. Just by imagining coloring the corners of a cube, and then counting how many there are, you can conclude that no possible strategy, no matter how clever you are, can work in all of the cases for this chessboard puzzle, if the number of squares isn't a power of 2. So even though it might seem to make it easier if you knock off a couple squares or reduce the size of the board, it actually makes the task hopeless. It also means that the solution to this puzzle, which I'll point you to in a moment, can be viewed as a particularly symmetric way to color the corners of a high-dimensional cube in a way that's disallowed in most dimensions. And if you're curious, I just couldn't resist showing this explicitly for a 4-dimensional cube. So in the same way that you can take a 3D cube and kind of squish it down into 2 dimensions, maybe with a little perspective, and get the same graph structure for how the vertices and edges are all connected, we can do the same thing projecting a 4-dimensional cube into 3-dimensional space and still get a complete view for how all of the vertices and edges are hooked together. If you wanted to try your hand at a weird sort of 4-dimensional cousin of a Sudoku, you could pause right now and try to figure out how to color these vertices in such a way that each of the 4 neighbors of any one represent all 4 different colors. Using essentially the same computation that solves the chessboard puzzle for the 4-square case, I can get the computer to explicitly draw that out for us. And at this point, when you're hopefully burning to know what the actual solution is, I'd like you to hop on over to Stand Up Maths, where Matt and I show you how it works. If any of you are somehow not yet familiar with Stand Up Maths, it is one of my favorite channels, run by one of my favorite people, so please do immediately subscribe once you land over there. I promise, you're in for quite a few delights with everything else he has to offer. Before explaining it, he and I simply walk through what it looks like for us to actually perform the solution. And as we do, I really want you to try thinking of the solution yourself, and to predict what it is that we're doing before we tell you. And if you're curious about the connection with Hamming codes and error correction, I'm definitely game to make a video on that, just let me know in the comments. I've been told that as far as motivating puzzles go, not everyone is as interested in symmetrical ways to paint a 64-dimensional cube as I am. But reliable data transmission? Come on, I think we can all agree that that's universally sexy.
Yeah, there you are. Oh, I've got my... Now that's a log. If a game involves aspects of randomness and chance, is it possible for one player to be so lucky while playing that game that we can say with mathematical certainty that they are officially too lucky? This is actually the most requested video topic I have ever had, because just over a month ago there was some big drama in the Minecraft community. One of the most popular players, someone called Dream, they've got over 15 million subscribers on YouTube. They're probably on Twitch as well, I don't know. But they were accused of cheating because in their Minecraft speedruns, they were having incredibly good luck. And because all the arguments against them, all the proof that they were cheating was based on probability and statistics, an overwhelming number of you got in touch with me and asked if I could take a closer mathematical look at it. And I was very happy to do so. And my goodness, there were some interesting results. Wait, a beard? How long did that take to film? I know a lot has already been said about the Dream speedrun controversy, but I think I'm actually quite well placed to make a video about it because I am a disinterested party. That's not to say I'm not uninterested, like I am interested in what's going on, but I haven't got an interest, like an investment in either of the two parties. So I'm disinterested, I don't care who's right, but I'm interested. I want to make sure we get to that right answer. And we're going to have a pretty wide spectrum of people watching this video. If you're here for the Minecraft, First of all, welcome to the channel. I'll try and go through the maths as clearly as I can. Also, cap.
The fastest way to obtain a number of key resources. They then head to the Nether, which is a different dimension, by traveling through a Nether portal. In a speedrun, that requires getting water from a river and lava from a lava lake. Don't try to understand the logic, just go with it. Once they're in the Nether, players can barter gold that they've mined with Piglin, who will give them different items, some of which will be ender pearls. The players then have to find a Nether fortress where they can kill blazes, and blazes will sometimes, when they die, drop a blaze rod. The ender pearls and the blaze rods means the player can now activate yet another portal, which will get them through to pretty much the end of the game. They pop out, there's a dragon they've got to kill, an exit portal, and then that's done. The credits roll. And the challenge of speedrunning is just to find the fastest way to do a certain combination of all these different things to get to the end of the game as quickly as possible. And traditionally, I tend to watch speedruns of classic games, things like Super Mario Brothers, where yes, there's some luck, like there's some randomness in the game, but it's mostly skill. I mean, even things like Mike Tyson's Punch-Out!, a very old game, watching people hone the skill required to do that is absolutely incredible. In Minecraft, while there is obviously a lot of skill, there's way more luck than you get in a lot of other speedruns. For example, when trading with a piglin, there are actually 17 different distinct items they might give you, and inside the game code, there's a table for the weights of how likely each of these different items are. If you want to get an ender pearl, you can see that's weighted 20, and 20 out of 423 gives you a probability of 4.728. Ish, roughly 5%. So you've got to do a lot of trades to get ender pearls. And if you start putting gold ingots on the ground, a piglin will stand there and sequentially trade until they've used up all of the gold. What you can do, little pro tip here, is if you put them in a bit of a hole, it'll stop them from wandering away when they're done. You can then go and start a parallel series of trades with a different piglin. And if you get them all going at once, eventually you should get enough ender pearls. And in the 6 live streams that Dream did from October 2020, across them there were 262 barters, and so you would expect on average 12 of those trades to result in ender pearls. Dream, however, got ender pearls from 42 of their barters. That's over 3 times the average. Blaze rods are a bit more simple. They occur 50% of the time you kill a blaze. Over the same 6 live streams, Dream killed 305 blazes, which should give you 152 or 153 blaze rods on average. Dream got 211. Dream was getting pretty lucky.
Now that we know precisely how lucky Dream was, the next step is to calculate what is the actual likelihood of someone being that lucky.
What is the probability that you get ender pearls 42 times from 262 barters? We can work that out using this, the binomial formula. I love it. It's such a good formula. It gives you the exact probability for a specific number of successes. In here, you put the probability of success. You then raise it to the power of how many successes you want. And here's the probability of failure, which is to the power of all the other times when you don't want a success. And the term out the front, that's the choose function, which compensates for the number of different ways you can arrange where the successes are. So like in this case, we don't care when people get the ender pearls, we just care how many they get. Using that formula, we can fill in a whole table to give you the probability that you will get any number of successful barters resulting in ender pearls, and we plot that. You can see the most likely is 12, up at 11.6% probability, and this middle clump between 1 and 24 successful barters is 99.9%. You are overwhelmingly likely to be in this part of the distribution. Whereas Dream is at 42 all the way out here. That has a probability of happening of 0.00, a bunch of zeros, 4. Although it's slightly deceptive when you're looking this far out to just pick one specific value, because there's so many other nearby ones it could be. So what we actually do is we look at the probability of getting this or better, which is the same number of zeros, but then 5, 6. I'm actually going to stop writing that as a percentage and just do it as a straight up number. The probability is 5.6 times 10 to the negative 12. And sometimes it's useful to think of that in terms of odds. And so that is a probability of 1 in 1.8 times 10 to the 11. We can now repeat the whole process for blaze rods, which have a 50% chance of happening each time you kill a blaze, and the probability of getting 211 or more blaze rods out of 305 kills is 8.8 times 10 to the negative 12. Also incredibly small, not dissimilar to the other one. And that represents odds of 1 in 1.1 times 10 to the 11. So that's 1 in 110 trillion. Very, very unlikely. And if we assume that these two probabilities are independent, the chance of them both happening, we multiply them together, and the overall probability is 5.0 times 10 to the negative 23. That's a 1 in 2 times 10 to the 22 chance. A 2 with 22 zeros after it. Getting a result as good or better than what Dream got is vanishingly unlikely.
But just the straight odds, that's clearly not the whole story. I mean, you're watching me sit here, have arguably better luck than I have any right to have. What are the odds of this happening? Is this real? Have I faked it somehow? Well, there's a lot of things you don't know. How long have I been sat here for? Where did this beard come from? How can we compensate for all the unknowns outside of the actual bit we're looking at? And don't worry, this is where more statistics and probability come in. And actually, it's a good time to go to the very first segment of this video, part 1, the attack.
Part 1, the attack. It all kicked off when Dream submitted one of their speedruns to speedrun.com. And it would have been, at the time, the 4th fastest speed run of this part of Minecraft in the world. However, the moderation team at speedrun.com were not convinced that Dream was using an original, unaltered installation of Minecraft. They thought the luck indicated Dream must be cheating. They had somehow changed the version of the game they were playing. And so they released a summary video that went through their investigation into the mathematics of the probabilities in a nice kind of introductory level. And they released a 29-page PDF that went through it in, I would say, a rambly level of detail. Their starting point was some observations from other speedrunners that Dream had had very good luck with the Ender Pearls and Blaze Rods across 6 consecutive live streams in October 2020. They then did the same calculation that we did with the binomial distribution, combined them the same way, and got the 10 to the negative 23 probability that we previously saw. But they didn't stop there. In fact, the vast majority of the paper is dedicated to looking at how there could be some kind of bias in their findings. They accounted for 4 different ways that their investigation into this probability could be unfair against Dream, and tried to compensate for all the unknown aspects of how Dream could have got this lucky. We don't have time in this video to go through all 4 of those, so I'm going to look mainly at sampling bias in stream selection. This is the idea that if Dream was doing a lot of different live streams, someone could have just maliciously picked the ones which made Dream look the most guilty. However, we can fix that with some mathematics, as I will demonstrate with a coin flipping example. Let's say I've uploaded a video to YouTube of me flipping a coin 100 times. Because I've done that. It's on my second channel. You can check it out. It's there in case you ever can't be bothered flipping your own coin. And I'm using a coin which is yellow on one side for heads and it's blue for tails. However, let's say, hypothetically, some malicious actor has edited out just a run of 12 flips from the middle where I got 10 tails out of 12 times I flipped the coin. And they're saying that clearly the coin can't be fair. If you do the binomial distribution on this, there's only a 1.6% chance that you'd get 10 tails out of 12 flips, or a 1.9% chance that you would get 10 or more tails out of 12 flips. Clearly, it can't be a fair coin if the chance of getting my results are so incredibly small. Now, you come along and you're not sure who's telling the truth here. So you're going to try and compensate for the fact that you know I did 100 flips. And let's say hypothetically you can't find the original footage. So yeah, I know Matt flipped it 100 times. And obviously this malicious actor has picked a run of flips with the smallest probability of having occurred if the coin was fair, like the p-value. But there were loads of other runs of flips they could have picked. Technically, they could have picked any of the individual flips. There's 100 of those to pick. They could have just cut one out. They could have picked any of the 99 pairs of flips. They could have picked any of the 98 runs of 3, any of the 97 runs of 4, all the way up. In fact, there are 5,050 different possible consecutive runs of flips this malicious actor could have picked. Now, at this point, to be honest, you've got the general idea. If you're looking at some results, you've got to bear in mind that there were probably more results which someone could have picked from, and you've got to somehow factor that in. The details of how we do this get difficult to follow, though, because you're taking lots of inverses of other inverses and you're rounding things up or down, and there's no way you can pick this all up